very nice analysis on lenticular galaxies that he is going to show now. And I want to personally thank Josep Tous in front of you because he accepted to switch his talk, which was planned by the end of December, and to move it forward because the speaker from this week couldn't make it. That's why you had the pizza seminar announcement a little bit delayed. And I want to personally thank his effort for presenting almost 1 month in advance. So thank you, Josep Luis. The floor is yours, and looking forward to hear your talk.
All right. Thank you, Elena, for this nice presentation. Can you hear me well?
Mm-hmm.
Okay, so I'm going to share my screen. And let me put that in presentation mode. All right. I just want to add that I'm very happy that you invited me to present my work here at your pizza seminars, and that I hope that we can really soon meet each other in person and have a coffee or maybe eat together and have an actual discussion face to face.
Yeah, I totally agree. It's time now.
Yeah, it's time. Well, anyway, let's talk about S0 galaxies. First of all, let's start from the beginning. What are these objects and what makes them so special? Well, these occupy a special position in the Hubble tuning fork diagram as they connect the branch of ellipticals and the branch of spirals, because they share intermediate characteristics between these other two main morphological families. They would be made by a central spheroid, which is the bulge, surrounded by a disk with no spiral structure and with very little amount of interstellar gas and dust. Regarding their baryonic content, they are classically conceived as passive objects, meaning that they form very few stars each year, and because of that, they would host old and red stellar populations. But what really makes these objects so interesting is that they are relatively abundant in both low density environments and high density environments. And because of this, their origin could be ruled by very different sorts of physical mechanisms. Actually, this is an old debate that is still alive, because many works trying to disentangle their origin have often reached inconclusive results or even contradictory between each other. So let me present you the two typical scenarios in which a lenticular galaxy can form. In the first one, we would be in the low density general field, where the isolated lenticulars we observe, we think they might proceed from a merger of two coplanar spiral galaxies, a major merger. A merger of such characteristics is thought to be able to erase the spiral structure of the parent galaxies. Also, it could trigger a starburst that consumes most of the cold gas that the galaxies had available to form new stars, and also to grow a central bulge. Mergers can occur in the low density general field because of the velocities at which the galaxies move are similar to the internal velocities of their stars. On the other hand, we would have the high density environments which occur in galaxy clusters, where these galaxies, lenticular galaxies or S0s, dominate in number. And there it may sound strange, but mergers are no longer effective. And this is because the velocities at which galaxies move through the intracluster medium are much larger than the internal velocities of their stars. So instead of gravity, we need to invoke other kinds of physics like hydrodynamic interactions to do the job of the transformation. A typical mechanism that it is invoked inside this galaxy, this structure of many galaxies, is the ram pressure stripping. This is, well, in these galaxy clusters, the lenticulars would be former spirals that, as they were falling through this hot and dense intracluster medium, the pressure exerted over the interstellar gas of their disks would remove this gas, and also it provokes that their disks become thicker. So these galaxies evolve passively as they no longer have material to form new stars. So until they become lenticular galaxies. So of course, we have evidence supporting each of these two mechanisms. For the first one involving gravity, for example, we find many lenticular galaxies that are isolated in low density environments that show these counter-rotating disks. That is, the stellar component would rotate in one direction and the gas component would rotate in the opposite direction. Or also we find an overabundance of the star-forming S0s among the population of double-peak galaxies, which is thought to be the final stage of a merger between two galaxies. And not to mention that they are often obtained in theoretical works that produce merger simulations with a great variety of orbit configurations, and even when this scenario is poor in gas. And supporting the other high density scenario, we have these beautiful images of jellyfish galaxies, which are observed inside the clusters that show this kind of filaments with star formation activity. And this shows how this pressure exerted by the hot and dense intracluster medium is able to remove all the gas from a galaxy that is falling. Or very often, the well-known morphology density relationship discovered by Dressler and that is observed inside clusters that are dynamically relaxed is often invoked as a sign that indicates that lenticular galaxies can be born inside the cluster of galaxies. This relationship consists in an increase of the fraction of S0 galaxies with the projected density at the same pace that the fraction of spirals plus irregular galaxies decreases. So this is a sign that there is a kind of transformation from spiral galaxies towards lenticular galaxies. So I hope that more or less at this point, you are convinced that such different mechanisms should yield their own imprint on the resulting objects, on the properties of the resulting galaxies. I think that this phrase would summarize quite well the main motivation behind my PhD thesis. And as I said at the beginning, this is a debate that is still alive because there is no consensus regarding the origin of these galaxies. Works that have been devoted to investigate these origins, especially using photometry, have not reached conclusive results. So what now? Maybe this imprint is more subtler, and maybe if we use a new approach using spectroscopic data, we would be able to find this imprint on the S0 galaxies. And this is precisely an approach that recently has been taken by some authors. Here I like to comment on two very nice works involving bulge to disk decomposition. A first one by Xiao 2016, in which they study around 600 nearby S0 galaxies. They split their sample a priori into active galaxies and other kinds of galaxies according to a BPT classification. And they find that the active population of S0 galaxies are mainly located in sparser environments, whereas at the same time, these star-forming galaxies would have lower stellar masses with bulges that are more like pseudo-bulges, meaning that they maybe are smaller than a classical bulge, and that are bluer and more metal-rich than their disks. Another work, this time involving integral field spectroscopic data, is that by Fraser, McKelvey and company 2018, which they study 300 nearby S0s, and they divide the sample, splitting each of the data cubes of the MaNGA into bulges and disks. And then they stack the spectra of each of these two structures and find that the population of S0 galaxies is actually made of two subpopulations with the mass, the stellar mass, as the main divider between the two groups. They also find that the massive, old, and metal-rich S0s would have classical bulges that would be older than their disks, as it is shown in this figure, whereas the less massive would behave the other way around. However, they don't find any correlation with environment, and note that they are not using the full spatial resolution of MaNGA, as they are grouping bulges and disks. And more recently, a work that may result familiar to some of you is that by Domínguez Sánchez et al. 2020, in which for a large sample of S0 galaxies, again using MaNGA data, they group their sample by the absolute luminosity and the central velocity dispersion, and then they stack all the spectra into radial bins for each of these cells to increase the signal to noise of the spectra they want to analyze. And this is because they measure Lick indexes to end up to compare them with synthesis of stellar population models and derive ages, metallicities, alpha enhancements, and other properties. They find agreement with the results from Fraser-McKelvey regarding the existence of two populations of S0 galaxies with a stellar mass as the main divider. And they also find that the more luminous would present strong gradients in age, but very flat profiles in metallicity, whereas the less luminous galaxies would behave more or less the other way around. More or less simultaneously, we wanted to contribute with our grain of sand to this cause. And before moving on to analyzing integral field spectroscopic data, we wanted to take all the possible profit from the single fiber spectroscopic data, as we realized that nobody else had done a work like the one we intended to do at that moment. So I think it was a perfect moment to carry on a work like this. So today I'm gonna present the highlights of this work, but also I will mention some notes on two other works in which we are involved. One would be a multi-wavelength study of the activity in S0, in the local population of S0 galaxies. This is led by a former student at the ICCUB, Cristina Jiménez Palau, that hopefully I think will join you as a PhD student next course. And also I will talk about the logical continuation from our work in 2020, for which we count with the help from Elena, which is applying the same methodology we used in 2020, but to analyze the MaNGA data. So let's talk about our approach in 2020. We analyzed a large sample of optical spectra of lenticular galaxies, nearby galaxies with redshifts below 0.1. And we took the morphologies from the classification by Domínguez Sánchez 2018. And thanks to those large numbers, we were able to build a volume limited subset of 32,000 S0s, which is very much, that give consistency and robustness to our statistical results. So now, for those who maybe are not so familiarized with this kind of big data approaches, I'd like you to imagine that each spectrum of a galaxy is like a vector with as many different variables as different wavelength values, right? Those coordinates allow to identify this galaxy in a space of as much dimensions as different wavelength values and allows us to identify it from the rest like a fingerprint. Well, if two galaxies have some properties in common, like for example, a similar stellar mass, or they share some common origin, they would look in this space of 4,000 dimensions more or less close to each other. Whereas if we have two galaxies that have nothing in common, they would be far away from each other in this space. So now you visualize the problem, our sample, like it is describing a cloud of data points in this space of many dimensions. And if there are some differences that are captured by the spectra of our galaxies, they should be visible in this cloud of data points. But however, it's better to look for those differences, choosing an optimal representation for this purpose. And this is what we do with a principal component analysis. This sort of analysis gives you some new axes. They are sorted according to the explained sample variance. And here I show you that together with the mean spectrum of our sample, that with the first three principal components, these three new axes, we are able to explain almost 95% of the sample variance, whereas if we use only the first two, we are talking about 90% of the sample variance. So we can reduce the dimensionality of the problem to a very low dimensional space of 2 dimensions. And this is what I show in the left-hand side of the screen. We can use the first two principal components to project our sample of optical spectra of S0 galaxies. And by doing so, we observe that our data is structured in 2 main spectral modes. One would be made by all the galaxies that sit within this kind of narrow diagonal band, which is very crowded, and another one much more scattered, made by all the data points that are expand towards the right-hand side of the plot. Because the galaxies in this narrow band show passive spectra with red continuum, we name this mode the passive sequence. And because the galaxies in the other mode show strong emission lines, we name this other mode the active cloud. So then we proceed to classify all the galaxies of our sample according to each of these 2 modes they belong to. And to do so, we use a combination of 2 algorithms. The first one is a logistic regression, which is basically a binary classifier, right, that yields this bimodal distribution of probabilities of belonging to the passive mode. And then to univocally distinguish the 2 modes, we find the 95% of the interclass variance between this distribution to define the 2 modes. So all in all, at the end of the day, we have that 70% of our sampled S0 galaxies would belong to the passive sequence mode, whereas a 25% would belong to the active cloud mode. And we have very few objects lying in between the 2 modes that we name transition region galaxies, and that I won't discuss them today. So now let's talk about the results we derive. First of all, we observed that there are some linear correlations between the coefficients of this projection and some of the main properties of these galaxies. For example, we see here that the strength of the H-alpha emission line varies almost perfectly perpendicular to this passive sequence mode, right? And something similar would happen with the 4,000 angstrom break, although not so neatly. And just to give a counterexample of a property that varies in an orthogonal direction to this one, we would have the stellar mass to light ratio that, as you can see, it is very disordered, but more or less is varying parallelly to this passive sequence mode. And this is actually a very good sign, meaning that our principal components have been able to capture actual physical differences. So now let's try to understand what is telling us the classification we have already done. We can define a new parameter, this delta PS, which is simply the distance of any of these points to the a fit that defines the core of the passive sequence. And if we look at the first plot, we realize that this parameter is simply sorting the galaxies according to the strength of their emission lines, or what is the same is sorting the galaxies by the level of their activity, sorry. But we are not able to distinguish whether this activity is coming from a healthy star formation or from the AGN, for example, or from both phenomena. So another property that allows to sort the galaxies by its star formation rate status is this delta MS. This is simply the distance of any galaxy to this purple line here. This distribution comes from representing the star formation rate against the stellar mass for all the main galaxy sample of the SDSS. This diagram allows to split the population, the whole population of galaxies into star-forming galaxies, which would be near the main sequence, this purple line. And here on top of that, we would have starburst galaxies. And also we have an intermediate region made, this is named as Green Valley, and is made by all the galaxies that are transitioning from the main sequence towards the region of the quenched galaxies. Here we would have passive galaxies that form very few stars each year. So now, sorry, I'm gonna move that. Let me share with you some new results from the work of Cristina Jimenez. I love this plot because it helps us to understand what's the composition of our spectral classes, right? Here we are representing the parameter delta PS against the parameter delta MS for our sample of S0 galaxies. The horizontal lines are our spectral classes represented in this parameter, right? And the vertical lines split the population by their star formation status. And here, in addition, we have included 90% counter plots that enclose the 90% of the population of star-forming, safer, and liner galaxies as classified by a VPT diagnostic diagram. This indicates the nature of their nuclear activity, nuclear emission, sorry. And we see that our active mode is made mainly by star-forming galaxies, right, from the main sequence, but also we find some in the region of the Green Valley and some in the region of quenched galaxies. But they are inside our group of active S0s because they most likely they show this safer emission, right? And also we can do more or less the same for the passive sequence, in which we find that most of the liner population would occupy this our passive sequence, and is made mainly by quenched and Green Valley galaxies. Anyway, let's go back to our work in 2020. Now let's have a look on the main properties of each of these two spectral classes. Let's have a comparison of the probability distribution functions. And first of all, we see that despite being significantly, statistically significant, the differences of these two populations in comparison to the rest of the distributions, these look pretty much the same, right? And this is something that contrasts with the works I was mentioning at the beginning. Then we also find that our active population hosts a younger, bluer, and poorer stellar populations than the passive counterparts. But perhaps the most striking difference that could have been anticipated by the plots I was showing you earlier is that the active population shows star formation rates which are one order of magnitude larger than the star formation rates of the passive counterparts. Sorry, here, and with average star formation rates that would be similar to the ones observed in late type spiral galaxies. Sorry, I'm moving this through the screen. Also related with this remarkable high level of star formation rate, we find differences in the content of the interstellar gas. For example, in the plot at the left-hand side of the screen, I am showing you the total amount of extinction in the V-band as function of the ICE-CSIC axis ratio, which is a proxy for the inclination of the galaxies. In the left, we would have edge-on systems, and in the right, we would have phase-on systems. And we see that the active population shows a clear dependence with the inclination, a clear dependence of the total internal extinction with the inclination. And this is not observed for the passive counterparts. I like very much this result because this is an independent proof that our spectral classification is working, because this comes from photometry alone, whereas our classification comes from analyzing the spectra and using a mathematical approach, the principal component analysis. Now, let's check the environment of these galaxies with our own density, local density estimator, this one here. And this plot in the right-hand side of the screen has 4 dimensions. I am showing you the fraction of active S0s as a function of the local density. And in color, I show you the strength of the H-alpha emission line, and the size of the data points would be proportional to the star formation rate of these galaxies. And we see that all these represented properties decrease linearly with the logarithm of the local density. So a final result from 2020 would be the one I am showing you in this plot. Here in gray, these are contour density contours of data points that show the distribution of our sample of S0 galaxies. And on top of that, I have overplotted a random sample of, I have used the same principal components of our lenticular galaxies to project the spectra of a random sample of around 10,000 spectra of each of the other main Hubble types, right? And here, this figure shows that our passive sequence S0 galaxies look similar to the elliptical galaxies from a spectroscopic point of view, whereas the active counterparts not only have a similar, are similar to late type spirals in the sense that they have similar levels of star formation activity, but the similarity extends to the whole optical spectrum. And this is somehow gives we think this comes from the fact that precisely the S0 galaxies show these intermediate characteristics between spirals and elliptical galaxies that I was saying at the beginning. So now let me devote some minutes to talk about our current approach. Now we are extending all this methodology I have already exposed to analyze MaNGA data for 600 lenticular galaxies. We are using, again, morphological classification, an updated version of Fisher 2019. Now, MaNGA, well, let's say that MaNGA, I'm not an expert, but I will try to explain more or less what we are doing. MaNGA applies bundles, these hexagonal bundles of fibers, to obtain the spectrum at different parts of the target galaxies. So if before we had only one single spectrum from the central part of the galaxies, we now have several dozens of spectra for each single galaxy. So we now proceed doing radial beams and stacking all the spectra that fall within each of these radial beams, going from the center to 1.5 effective radius. So to the problem we had before, we are adding one extra dimension, the spatial, the radial dimension, right? So again, we apply a principal component analysis, and surprise, surprise, what we find is that the principal components for the MaNGA radial stacks look very much the same as the ones we derived in 2020, as these tiny residuals show, right? Here we see that most of the differences accumulate in the mean spectrum, but for the first three principal components, the residuals are very small. And we have quantified this equivalence using a Bayesian approach, and we have found a very good correspondence up to order 5. And also this proves that in our first approach, the aperture effects were minimal, because before we were using a single fiber with a finite aperture, and now we are using the light from more surface of the galaxies. Anyway, now when we use the first three principal components to project these radial stacks, instead of having one single point, we have more or less 15 points for each galaxy. So this describes a spectral radial profile of our S0 galaxies. And here, each of these data points would represent the radial composite spectrum for each galaxy. And however, this is still too complex to look for differences if we do a plot like this for the whole sample. So we derive, or we fit vectors to these radial profiles, and we used their spherical coordinates to summarize these vectors. And now, just to give you some examples of the kind of things we're working on, we can look, for example, at the length of these vectors, which is the modulus of these vectors, right? And we are observing actual differences between the two subpopulations here. This would tell us that for our active population, the spectral variation would be more important than for the passive counterparts, and also that the active population of S0 galaxies would concentrate around 2070 degrees, 270 degrees, sorry. And this translates into that the active population would show, would have an activity that decreases outside IM. And this is clearly shown in the last plot on the top part of the screen in the right-hand side, in which I show you the median distance to the passive sequence, this parameter I defined it earlier, as a function of the radius of these galaxies for each of the three main populations of galaxies. And you see how this parameter decreases for the active components. So let me just go through the summary of our contribution. In 2020, we carried out what would be the most extensive and unbiased statistical study of the global photometric and spectroscopic data of the S0 galaxies in the local universe. And with this, we were able to unveil two populations of S0 galaxies. We would have that 70% of them would conform to the classical view that S0s are passive systems, whereas 25% of them would present active spectra with star formation rates that would be equivalent to the ones measured for galaxies, late type galaxies like the Milky Way, for example. And this is a confirmation of previous findings that not all lenticular galaxies are red and dead objects. All this suggests that there is not a one-to-one relationship between morphology and spectral class, and this suggests that there are different timescales for the dynamic and star formation processes. And also we find that for the active population, there is a linear decline with the local density that goes in parallel with the star formation and the strength of the H-alpha emission line. And right now, we are working with MaNGA data. We are extending all these analyses to study the spectral radial profiles of a sample of S0 galaxies. With this, we have found that the principal components of the single fiber SDSS spectroscopic data are equivalent to the principal components of the MaNGA radial stacks. And this supports our previous work and tells us that the aperture effect we had was minimal. Also, it tells us that we can extend what we learned from 2020 to the work we are carrying on right now. And we are gathering this information and we are working on the interpretation of all these radial spectra. So I think that it would be all. Thank you very much for listening to me. And I would be happy to discuss with you now or later on by email. Thank you very much.
Thanks a lot, Josep. That was an excellent talk. Believe it or not, even myself, I learned a little bit more about lenticular galaxies. And thanks a lot also for sticking perfectly to the time. So we have some time for questions. If you have any questions, please raise your hand, write them in the chat, or even speak up. Questions are always difficult in the first minutes, so I'll give some more time for the shy ones. Think about your questions. Okay, if not, I will start with one myself. So you said that you didn't find in your sample the separation between active and the active cloud and the passive sequence in terms of the mass or magnitude as myself and Kevin McPherson did. So did you check how does the mass or the absolute magnitude plots in the principal component plot?
Yes. How? Sorry, can you repeat? How?
Yeah. So the question I posed it very wrongly. I will ask again. Did you check, and if so, do you remember how does the magnitude or the mass distribute along the principal component plots. So you see that the H alpha moves in this direction and the mass to light ratio moves in this direction. Does the absolute magnitude, is it ordered? Does it follow any distribution?
Yeah, that was one of the first things we look at, and we see that this property was very mixed in this plot of PC1, PC2. Let me go back to this slide. Sorry, I'm gonna make you smaller. Here, yeah, we see that this property was very disordered in this plot. Right, maybe the stellar mass to light ratio would present some degree of order, and we think we have this problem because when we look at these differences, we are using a volume limited subset, right? That this limits the low mass galaxies. We are excluding the low mass galaxies here, and we don't have them here. And maybe this difference on the mass would show up if we included these low mass galaxies.
Okay, but even if you have a small range of mass, there's no order in that.
No,
you don't see any order.
Unfortunately, not.
Well, I don't think that's unfortunate. That's really interesting, in fact, right? Because we tend to always think about this bimodality of galaxies, and the mass is one of the main properties that divide these two types. So it's very interesting to see that mass is not playing a role, but still you find such a different properties on these two groups. So I think that's very interesting.
Yeah. Let me add just one thing. Remember that our classification is a spectral classification. So we have found that the property that matters more in this classification is precisely the star formation rate. And this classification is sorting the galaxies according to the activity, but we are missing somehow the mass here.
Okay, good point. Are there any other questions in the audience? No? No questions for Josep? He gave a beautiful talk. Okay, so I have a few more, but then I think we can discuss them in person in our next meeting.
Okay.
So
thank you very much.
Thanks a lot for your beautiful talk again. And for the rest of you, have a great weekend and see you in the next session of the Pizza Seminar. Bye.
Thank you. Bye-bye.